Alright, it's quite simple really with this integral right here, 1 over x squared, and then from the interval -2 to 1. So we can actually rewrite this integral as from integral from -2 to 1 of x minus 2 dx, and then we can integrate this. We get that it's plus 1, and then divide by -1, so it becomes -x minus 1, or rewrite this as -1 over x with our bounds from -2 to 1. Then evaluate that, so -1, 1 minus -1, and then -2. So this will become -1. Negative times negative is a positive, and then subtract that, and then you get that'll be minus 1/2, and then that'll be equal to -3 over 2, which is our integral for this. So if you can check this to verify it yourself, it should come down to this. So if you do end up with an answer of -3 over 2, I would just like to say that answer is incorrect. Yeah, it's incorrect.
Got him!
Okay, so why don't I say that really? Okay, so why don't we first actually sketch out this function, 1 over x squared. I'm gonna be, I just dropped my eraser. Let's sketch our function so I can get this cap open. Okay, that's such a struggle, right? Just open a cap. Anyway, we sketch the function 1 over x squared, like so. It's not accurate, but just bear with it. And then we're defining it from the interval between -2 to 1. So this little area right here is the area we're trying to compute. Oh, but it appears to be that because this is a rational function, there's a vertical asymptote that exists at 0. So that means this area is not finitely computable. So how do we? So how is there a way to evaluate this integral specifically? Well, one way to look at it is this is actually considered like a improper integral, meaning you either have a integral that will either be convergent, such as that the integral will be computed as a finite number, or divergent, whether it's evaluated either between from either negative infinity or infinity. So we're gonna let's actually rewrite this integral as I'm gonna use this marker instead. So let's actually split this into limits. So here we have a vertical asymptote at 0 here. It's just like so, because 1 over x squared, it's undefined at 0 at x. And then let's say we take the left limit, so we can write this as 0 minus, and then same thing for 0 plus. It's just based on what we learned from learning our limits from taking a look at the inspection from the left side and the right side. So let's split this integral into 2. We have -2 to 1 of 1 over x squared dx. And because we're taking limits, we're taking limit as it approaches from 0 from the left and 0 from the right, we can rewrite this limit as so, right? As let's just define this letter as b as it approaches 0 from the left of the integral from it starts at -2, and then this is b of 1 over x squared dx, and then plus the limit as we're gonna call the right limit 0 plus a, as a approaches 0 plus of the integral from, and then starting from the left, starting from this is 0 plus, or we define it as a, to 1 of 1 over x squared dx. So let's first investigate the integral inside. So it's straightforward. It's just simple computations. It's just take the integral of this. So we found that the integral from 1 over x squared is negative 1 over x. So I'm gonna write this as the limit as b approaches 0 from the left of negative 1 divided by x from our bounds of b to negative 2. And then if we evaluate this, we have negative 1 divided by b, and then subtract negative 1 divided by negative 2. And so we have negative 1 over b plus, well, the negative over negative, that's a positive, and subtract, so it becomes minus 1/2. And then now let's evaluate for this side. We'll get to the limit portion in just a sec, but I just want to compute these integrals just for time's sake. So let's write this as the limit as a approaches 0 plus from the right side right here. And same thing, the integral of this is negative 1 over x. Evaluate from the bounds from a to 1. And so this will be negative 1 divided by 1 minus negative 1 divided by a, and this is equal to negative 1 divided by 1 is negative 1, and then plus 1 over a. So now that we have this, so let's just put this back into the parentheses. Oops. So we have the limit as b approaches 0 minus of negative 1b minus 1/2, and then the limit as a approaches 0 from the right side of, what is it, negative 1 plus 1 over a. So it's simply just plugging 0 minus into b, but observe that when you have a non-zero constant divided by a number 0, you either have two options. You could either approach one from negative infinity or positive infinity. So we're saying b approaches 0 from the left, so we're taking some number that is very, very close to 0, but this is from the negative. This is for part of the negative number, so it could be negative 0.0000000 and so on 1, and it'll become. It turns out that when you plug this in, we get that it's negative infinity. So so it'd be negative times negative. So this will be a positive infinity. And then same thing with this one, negative 1 plus 1 over a. We take a 0 from the right side, as I said before, the positive 0.00000 so on, and then 1, and it comes down that it'll just be it comes 1 over that certain number. 0 from the right becomes infinity, so negative 1 plus infinity is just infinity. Let me redraw that infinity. It kind of looks a little weird. So the conclusion we can draw here is that because this is infinity and this is infinity, this means that it diverges. This diverges, and also this diverges as well. So now that we have that, this means that this entire integral over here is divergent. So our final answer is that the integral from negative 2 to positive 1 of 1 over x squared dx diverges. There is no finite number because it is not convergent, it is divergent. So that is all your answer has to be, it's just this. And simply because when we solve for one part of the equation, when we say it diverges, then the whole integral itself diverges. It wasn't really necessary to solve the other case, since if one piece of it is divergent, then the whole thing becomes divergent itself. So yeah, this integral is somewhat kind of like innocent looking, because the first thing that you would come to mind is simply just performing a simple like integration like so. But if you take a look at the graph closely, it's nothing but just a lie. So it's also good to draw your functions and then make some inspections and some observation of what the area really looks like in perspective. So yeah, this one's pretty interesting one, so that's why I chose this one. So yeah, that is all for this video. Thank you guys for watching. Feel free to check out the previous video I did, which was the what was the last video I did? Oh, I solved that Wi-Fi passwords. And also I just realized that I went back to that old video. I kind of messed up on the thumbnail. I think I accidentally put a plus beside the x cubed and a cosine x over 2. So yeah, that was pretty much that's kind of embarrassing. But feel free to check that out. Feel free to check out some of the other math videos I did in the past, and like, comment, subscribe, and I'll see you guys in the next one. Be careful when you see improper integrals like this. It's something just keep a heads up on. That's all I gotta tell you.